Hello there, and welcome to the Sleepy Science Society. Tonight, we're drifting into one of Earth's most patient and profound transformations. We're exploring valleys, those quiet depressions that wind between mountains, stretch across plains, and carve their stories deep into the skin of our planet. If you find comfort in these gentle explorations of our world, I invite you to like and subscribe. It helps others discover this peaceful corner where science meets rest, one sleepy soul at a time. But for now, let your breathing slow, allow your shoulders to drop, and prepare to wander through geological time as we uncover how valleys come to be. Valleys are among the most familiar features of Earth's surface, yet they hold within their contours the accumulated work of forces acting across spans of time almost too vast to comprehend. They are the spaces between, the low roads where water gathers, the sheltered corridors where civilizations have taken root for thousands of years. And they are, above all else, testaments to the relentless creativity of erosion, ice, and the shifting plates beneath our feet. When you stand in a valley and look up at the slopes rising on either side, you are witnessing a story written in stone and soil. Every curve of the valley wall, every twist in its course, every waterfall plunging from a hanging tributary, speaks of processes that unfolded long before human eyes existed to see them. Valleys form through the patient subtraction of material, grain by grain, boulder by boulder, through the slow grinding of glaciers, the persistent flow of rivers, or the sudden rupture of the Earth's crust itself. The formation of a valley is rarely the work of a single process. Instead, valleys emerge from a conversation between multiple forces, each contributing its own signature to the final form. A valley might begin its life as a crack in newly uplifted land, then spend millions of years being deepened by a river, only to be transformed again when glaciers advance during an ice age, widening and reshaping what the water had carved. After the ice retreats, rivers might return, flowing through a valley that no longer quite fits their scale, continuing the endless work of modification. Tonight, we'll travel through the many ways valleys come into being. We'll watch rivers cut downward with patient determination. We'll follow glaciers as they bulldoze through mountain terrain with the weight of thousands of feet of ice. We'll witness the Earth's crust crack and pull apart, creating rifts that stretch for thousands of miles. And through it all, we'll discover that valleys are not static features frozen in time, but dynamic landforms that continue to evolve even as we sleep. As you settle deeper into comfort, imagine standing at the headwaters of a young stream high in the mountains. The water here is vigorous, tumbling over rocks, cutting into the bedrock with every flood. This is where valleys begin their long journey toward the mud. See, and where we'll begin ours into the heart of geological transformation. The nature of valleys, understanding the basics. Before we can truly appreciate how valleys form, we need to understand what they are. At its simplest, a valley is an elongated depression in the Earth's surface, a low area typically running between higher ground such as hills or mountains. But this simple definition barely scratches the surface of what valleys represent. They are drainage paths for water, ecosystems unto themselves, and repositories of sediment that record the environmental conditions of ages past. Valleys are characterized by their length exceeding their width. They have a defined slope that runs along their entire length, generally descending from higher elevations toward lower ones. Whether a valley is a narrow gorge squeezed between towering cliffs or a broad floodplain stretching for miles, this fundamental characteristic remains. The valley has a direction, a gradient, and a story of how it came to be. The timescales involved in valley formation stretch human comprehension. While a single catastrophic flood might noticeably alter a valley's character in a matter of hours or days, the fundamental architecture of most valleys develops over thousands, hundreds of thousands, or even millions of years. A river valley in a mountain range might take 1,000,000 years to cut down just a few hundred feet through resistant bedrock. A glacier might require 10,000 to 100,000 years to transform a V-shaped river valley into a U-shaped glacial trough. The Great Rift Valley in East Africa, created by tectonic forces, has been forming for more than 20 million years and continues to widen even today. These vast timescales mean that valleys are remarkably persistent features of the landscape. Even after the forces that created them have ceased, after rivers have changed course or glaciers have melted away entirely, the valley form remains. You can walk through glaciated valleys in places where no ice has existed for more than 10,000 years and still see the unmistakable signatures of glacial action preserved in the rock. The shape endures long after the sculptor has departed. Throughout human history, valleys have been places of profound importance. They offer flat or gently sloping land suitable for agriculture. They provide natural routes for travel and trade, connecting different regions with relative ease. Rivers flowing through valleys supply water for drinking, irrigation, and power. The valley walls often shelter settlements from harsh winds, while the valley floors accumulate fertile soils washed down from the surrounding highlands. When you trace the path of human civilization, you often find it following the courses of valleys, those welcoming lowlands where life could take root and flourish. Valleys also serve as crucial components of Earth's hydrological cycle. They channel precipitation from vast areas toward the sea, organizing the chaotic flow of water into ordered networks. Small valleys feed into larger ones, which in turn feed into still larger valleys, creating hierarchical drainage systems that can span entire continents. The Amazon basin, the Mississippi drainage, the valleys of the Ganges, all are vast networks of interconnected valleys that gather water from enormous territories and funnel it toward the ocean. But beyond their practical importance to water and to human settlement, valleys matter because they reveal Earth's processes at work. Each valley is a record, a document written in landforms that tells of uplift and erosion, of ice ages and warming periods, of tectonic movements and volcanic activity. Learning to read valleys is learning to read Earth's autobiography, understanding how the planet has shaped and reshaped itself through deep time. When geologists examine a valley, they see more than just a depression in the ground. They see the accumulated evidence of forces that have been sculpting the landscape for eons, and they can work backward from the present form to reconstruct the history that created it. The three primary mechanisms of valley formation are fluvial action, which means the work of rivers and streams. Glacial action, the carving power of moving ice. And tectonic action, the breaking and shifting of Earth's crust. Each produces distinctive valley forms, though in nature, these processes rarely work in isolation. A single valley might show evidence of all three, its current form reflecting a complex history of different forces acting in sequence or even simultaneously. As we move forward through the night, we'll explore each of these mechanisms in detail, understanding not just what they do, but how they do it. We'll see how the character of the rock matters, how climate influences valley development, and how even the smallest details of a valley's shape can reveal the forces that created it. The story of valley formation is ultimately a story about time, patience, and the immense power that can be wielded by forces acting slowly but without ceasing. River valleys, the patient carvers. The most common valleys on our Earth are those carved by rivers. These are the familiar V-shaped valleys you can find in nearly every mountainous or hilly region. Valleys where a stream or river flows along the bottom, continuously working to cut deeper into the landscape. River valleys form through a process called fluvial erosion. And understanding this process is understanding one of the most fundamental ways Earth's surface transforms over time. Imagine a newly uplifted landscape, perhaps a mountain range just pushed up by tectonic forces. Rain falls on these fresh slopes, and water begins to flow downhill under the pull of gravity. At first, the water moves as thin sheets across the surface, but quickly it begins to concentrate into small channels. These channels become streams, and streams join together to become rivers. From the very beginning, these flowing waters start to erode the land they cross. Rivers erode through several mechanisms, and all of them work together to carve valleys. The first and perhaps most important is called downcutting or vertical erosion. This is the process by which a river deepens its channel by wearing away the bedrock or sediment at its base. The water itself exerts a force called hydraulic action. As it flows, it presses against the channel bed and walls, and this pressure can dislodge particles of rock and soil, particularly if the rock is already weakened by weathering or cracking. But water rarely works alone. Rivers carry sediment, everything from fine silt to large boulders, depending on the river's energy and velocity. This sediment acts as tools, grinding and scraping against the channel bed in a process called abrasion. Picture the river bottom as a surface being constantly worked over by sandpaper, except the sandpaper is made of sand, gravel, and rocks being dragged along by the current. Over time, this abrasive action wears away even very hard rock, slowly lowering the elevation of the river channel and deepening the valley. In the upper reaches of a river system, where the gradient is steep and the water flows rapidly, vertical erosion dominates. The river is young, energetic, and focused on cutting downward. The valley it creates is narrow and steep-sided, forming that characteristic V-shape. The river hasn't had time yet to widen its valley significantly, so the channel occupies most or all of the valley floor. The valley walls rise sharply on either side, and the cross-section, if you could slice through the landscape and look at it edge-on, would show that distinctive V profile. Why V-shaped rather than U-shaped? The answer lies in how rivers distribute their erosive energy and how the valley walls respond to the deepening channel. As the river cuts down, it creates increasingly steep slopes on either side. These slopes are subject to weathering, the breakdown of rock through exposure to air, water, temperature changes, and chemical reactions. Weathered material becomes loose and unstable, and gravity causes it to move downslope through various processes collectively called mass wasting. This might be as dramatic as a landslide or as subtle as the slow creep of soil down a hillside. The result is that while the river cuts straight down, the valley walls are gradually worn back at an angle. The steepness of that angle depends on the type of rock, the climate, and how quickly the river is cutting down. In hard, resistant rock like granite or quartzite, the valley walls can remain very steep, creating deep, narrow gorges. In softer rock like shale or heavily fractured stone, the walls develop gentler slopes and the valley is broader even while maintaining its V shape. The point is that the V shape arises from the combination of vertical erosion at the valley floor and the weathering and mass wasting that attack the valley sides. As you follow a river downstream, its character changes. The gradient becomes less steep. The water still flows, but more slowly, less turbulently. The river's energy is spent less on cutting down and more on moving sideways. This lateral erosion causes the river to widen its valley. The river begins to swing back and forth across the valley floor in a pattern of curves called meanders. On the outside of each curve, where the water flows faster, erosion is stronger, and the river eats into the valley wall. On the inside of each curve, where the water slows down, sediment is deposited, building up the valley floor. Over time, this meandering can dramatically widen a valley. The river doesn't just flow in a straight line down the center of the valley it has carved. Instead, it wanders from side to side, its meanders gradually growing larger and migrating across the valley floor. As it does so, it undercuts first one valley wall, then the other, slowly pushing them farther and farther apart. The V-shape might persist in cross-section, but now it's a much broader V, with the valley floor occupied by a sinuous river channel and the floodplain on either side. In the upper courses of river valleys, you often find features called interlocking spurs. These are ridges of high ground that project into the valley from alternating sides, creating a zigzag pattern. They form because the young river doesn't have the power to erode straight through hard rock ridges, so it takes the path of least resistance, flowing around obstacles rather than through them. The spurs appear to interlock when you look up or down the valley, each one partly concealing the one behind it. As the valley matures and the river gains more erosive power, these spurs might be worn back or even cut through, straightening the valley's course. The floor of a mature river valley is often covered with sediment called alluvium. This is material that the river has eroded from upstream and then deposited when its velocity decreased. During floods, when the river rises above its normal channels, and spreads across the valley floor, it deposits layers of sediment. Over many thousands of years, this process builds up a thick accumulation of alluvium, creating the flat floodplains that characterize the lower reaches of river valleys. These floodplains are incredibly fertile because each flood brings new sediment rich in minerals and organic matter, which is why river valleys have been such attractive locations for agriculture throughout human history. The development of a river valley is also influenced by something called base level. This is the lowest elevation to which a river can erode. For most rivers, the ultimate base level is sea level, since that's where rivers ultimately discharge their water. A river cannot cut its channel below sea level because water flows downhill, and once you reach sea level, there's no more downhill to go. As a river approaches its base level, its gradient decreases, its velocity slows, and its erosive power diminishes. The river transitions from cutting down to spreading out, from carving a valley to building a floodplain. But base level can also be local rather than ultimate. A lake along a river's course acts as a temporary base level for the river sections upstream from it. The river cannot cut down past the level of the lake until the lake is filled with sediment or drained. A layer of very resistant rock can act as a temporary base level, creating a waterfall or rapids where the river flows over it. Only after long ages of erosion, when the resistant layer is finally cut through, can the river resume downward erosion below that point. The longitudinal profile of a river valley, meaning the shape of the valley floor as you trace it from headwaters to mouth, is typically concave upward. It's steep in the upper reaches, where the river is far above base level and has lots of potential energy to convert into erosive power. It gradually becomes gentler as you move downstream, creating a smooth curve that reflects the river's adjustment to base level. This profile is not static. If the land is uplifted by tectonic forces, the river will respond by cutting down more vigorously, steepening its gradient and deepening its valley. If sea level drops, effectively lowering the base level, the river will similarly resume down-cutting. The profile reflects the ongoing balance between uplift, which creates elevation difference, and erosion, which works to eliminate it. Sometimes rivers cut through landscapes in ways that seem to defy logic. You might find a river flowing through a mountain ridge rather than around it, creating a narrow canyon called a water gap that cuts straight across the trend of the surrounding topography. These transverse valleys form through several possible mechanisms. The river might have been there first, flowing across a relatively flat landscape, and then the mountains were uplifted beneath it. As the land rose, the river cut down at the same rate, maintaining its course even as mountains grew around it. This is called antecedent drainage. Alternatively, the river might have eroded headward along a zone of weakness like a fault, eventually breaking through a ridge and capturing the drainage from the other side. Or the river might have been flowing on top of younger rock layers that have since eroded away, and as it cut down, it became incised into older structures that lie beneath. The valley's path was established before the true structure of the land was revealed. The point is that river valleys are not passive features. They are dynamic, evolving, responding to changes in climate, rock structure, tectonic activity, and sea level. A river valley that looks permanent to our brief human perspective is actually in constant flux on geological timescales, always adjusting, always cutting, always moving material from higher elevations to lower ones in the grand work of wearing down the continents. As you drift deeper into relaxation, picture a drop of rain falling on a mountaintop. It begins a journey that might take days or weeks or months, flowing downhill, joining with other drops to form a trickle, then a stream, then a river. And as it flows, it moves, it carves, it transports. It is part of a process that has been shaping valleys for as long as there have been continents and rainfall. The work continues, grain by grain, in mountain streams all over the world. Glacial valleys, nature's bulldozers. If river valleys are the patient work of water carving stone over immense spans of time, glacial valleys are something altogether more dramatic. Glaciers are often called nature's bulldozers, and the comparison is apt. These vast rivers of ice, thousands of feet thick and moving under their own immense weight, reshape landscapes with a power that rivers cannot match. The valleys they create are distinctive, unmistakable, and some of the most spectacular landforms on Earth. A glacier forms when snow accumulates faster than it melts, building up layer upon layer, until the weight of the snow begins to compress the lower layers into ice. As more snow falls and the ice thickens, the mass eventually becomes so heavy that it begins to deform and flow under its own weight, very slowly sliding downhill or spreading outward. In mountain regions, these glaciers flow down valleys, confined by the valley walls. These are called valley glaciers or alpine glaciers, and they are the sculptors of the great U-shaped valleys we'll explore. Glacial valleys are distinctive because of their shape in cross-section. Unlike the V-shaped profile of a river valley, a glacial valley is U-shaped, with steep, nearly vertical walls and a broad, flat floor. This shape is so characteristic that geologists can identify former glaciation just by looking at valley profiles. The U-shape arises from the way glaciers erode, which is fundamentally different from how rivers work. When a glacier moves through a valley, it doesn't just erode the bottom. The ice is so thick that it fills much or all of the valley, pressing against both the floor and the walls. The erosive force is distributed across the entire width of the valley, not just concentrated in a narrow channel like a river. As the glacier flows, it acts like an enormous file or rasp, scraping and grinding against everything it touches. This produces erosion that is both deep and wide, carving out that distinctive U-shaped trough. Glaciers erode through two primary mechanisms. The first is called abrasion. As the glacier moves, rock fragments frozen into the base and sides of the ice act like sandpaper on a colossal scale, grinding against the bedrock beneath and around the glacier. The ice itself is not particularly hard, but the rocks embedded in it are, and they scrape, scratch, and polish the bedrock surface. If you visit a formerly glaciated valley, you can often see the evidence of this abrasion in the form of glacial striations, long scratches carved into the bedrock by rocks dragged along in the ice. These striations point in the direction of ice flow, providing a record of how the glacier moved even though the ice itself vanished thousands of years ago. The second major erosional process is called plucking or quarrying. This occurs when glacial ice seeps into cracks and joints in the bedrock and then refreezes. When water freezes, it expands, and this expansion exerts tremendous pressure on the surrounding rock, wedging the cracks wider. As the glacier moves forward, it can literally pluck blocks of rock from the valley floor and walls, incorporating them into the ice. These plucked blocks then become tools for further abrasion, and the cycle continues. Plucking is particularly effective in well-jointed rock, where there are lots of natural planes of weakness that the ice can exploit. The combination of abrasion and plucking allows glaciers to erode at rates that can exceed what rivers accomplish. A large valley glacier can remove enormous volumes of rock, deepening a valley by hundreds or even thousands of feet. The Kali-Gandaki River Valley in Nepal, one of the deepest valleys on our Earth, owes much of its tremendous depth not just to river erosion, but to the work of glaciers during ice ages. Valley glaciers typically form in areas that were already valleys before glaciation occurred. Often, they inherit V-shaped river valleys carved during warmer periods. When climate cools and glaciers form, they follow these pre-existing valleys, taking advantage of the natural low paths through the mountains. As the ice flows through these valleys, it modifies them dramatically. The narrow V-shaped river valley is widened and deepened. The interlocking spurs that force the river to meander back and forth are simply ground away, truncated by the immense power of the ice. The glacier doesn't have to wind around obstacles the way a river does. If there's a rock spur in the way, the glacier erodes it, straightening the valley's course. This straightening and widening transforms the valley's character. After the ice melts, what remains is a much broader, straighter valley than existed before. The walls are steep, sometimes nearly vertical, especially if the rock is hard and resistant. The floor is relatively flat, often covered with debris that the glacier deposited as it melted. This debris is called glacial till, an unsorted mixture of everything from fine clay to massive boulders, all dropped in place as the ice that carried it disappeared. The flat floor of a U-shaped valley often has an irregular surface, with bedrock bumps and hollows. Sometimes these hollows fill with water, creating ribbon lakes, long narrow lakes that lie along the valley floor. These lakes form in areas where the glacier eroded more deeply, perhaps where two glaciers met and their combined erosive power carved an extra deep section of valley. Or where the bedrock was softer and wore away more easily. The thickness of the glacier is crucial to understanding how glacial valleys form. The thicker the ice, the greater the pressure at its base, and the more erosive power the glacier possesses. The main valley, where the glacier is thickest, erosion is most intense. But tributary valleys, where smaller glaciers flow in from the sides, have thinner ice and erode less rapidly. This differential erosion has important consequences. When the ice melts, the main valley has been deepened much more than the tributary valleys. The result is that the tributary valleys are left hanging high on the walls of the main valley, their floors elevated well above the floor of the main trough. These are called hanging valleys, and they're one of the most distinctive features of glaciated terrain. Rivers, or streams that form in these hanging valleys after the ice retreats, must plunge down to reach the main valley floor, creating spectacular waterfalls. Bridal Veil, Fall, and many other waterfalls in Yosemite Valley in California cascade from hanging valleys left by ancient glaciation. The movement of ice through a valley is not uniform. In the center of the glacier, away from the valley walls, the ice moves faster. Along the edges, friction with the valley walls slows the ice down. This differential movement creates stresses within the ice, causing it to crack and form crevasses. But beneath the surface, at the base of the glacier, something else happens that is crucial to understanding glacial erosion. The immense weight of the ice increases pressure, and increased pressure lowers the melting point of ice. At the base of a thick glacier, even though the temperature might be below the normal freezing point, the ice can partially melt under the pressure, creating a thin layer of water between the ice and the bedrock. This meltwater acts as a lubricant, allowing the glacier to slide more easily over the bedrock. This sliding, combined with the internal deformation of the ice, allows glaciers to move at rates of several feet per day in some cases, though the average is much slower, perhaps a few inches to the few feet per day. But even this slow movement, sustained over thousands of years, allows glaciers to transport immense amounts of material and carve valleys of extraordinary depth and scale. When glaciers finally retreat, which they inevitably do as climate warms, they leave behind a transformed landscape. The U-shaped valley remains, a permanent signature of the ice that once filled it. The valley might now contain a river, but it's typically a small, underfit stream, a misfit that seems far too small for the enormous valley it occupies. This is because the valley wasn't carved by this river. It was carved by a glacier hundreds or thousands of feet thick, and the current river simply inherited the valley after the ice departed. In many parts of the world, particularly in high latitudes and at high elevations, you can see glaciated valleys, even though the glaciers themselves have long since vanished. The valleys of the Alps, the Scottish Highlands, the mountains of Norway, the Sierra Nevada in California, the Himalayas, the Andes, all bear the unmistakable marks of glaciation. The U-shaped valleys, the hanging valleys with their waterfalls, the truncated spurs, the Reben lakes, all tell the same story of ice advancing and retreating, carving and shaping, leaving behind some of the most magnificent landscapes on Earth. And in a few places, glaciers still persist, actively carving valleys even today. In Alaska, in parts of the Andes, in the Himalayas, in Greenland and Antarctica, you can witness glaciation as an ongoing process rather than a relic of the past. These glaciers are natural laboratories where scientists can observe and measure how ice shapes the land, providing insights that help us understand the valleys carved by glaciers that melted away 10,000 or more years ago. As you relax deeper, imagine the slow, inexorable grinding of ice against stone. Picture a valley filled edge to edge with ice, the glacier moving down slope so slowly that you could never see the motion, yet moving nonetheless, scraping, plucking, reshaping the valley inch by inch, century by century, millennium by millennium, until the valley is transformed. The dance of ice and rock. To truly understand glacial valley formation, we need to explore in more detail the fascinating and complex ways that ice moves and erodes. Glaciers seem static, especially when you look at photographs, but they are actually in constant motion, flowing like extremely viscous rivers. This flow is what gives them their erosive power, and understanding it is key to understanding the valleys they create. Glacier movement occurs through two main mechanisms. The first is internal deformation. Ice, despite seeming solid and brittle, can actually flow over long timescales when subjected to sustained pressure. Under the weight of hundreds or thousands of feet of ice pressing down from above, the ice crystals at depth slowly deform and slide past each other. This is similar to how a very thick honey might flow, or how metal under constant pressure can slowly bend. The ice doesn't melt. It remains frozen, but it deforms, allowing the glacier to flow downhill under the pull of gravity. The second mechanism is basal sliding. As mentioned earlier, the pressure at the base of a thick glacier can cause ice to melt even when temperatures are below normal freezing point. This creates a thin film of water between the ice and the bedrock. The glacier can then slide over this water layer, much like a sled sliding on a thin film of water created by friction. This basal sliding can be intermittent, speeding up and slowing down in response to changes in meltwater production. But when it occurs, it significantly increases the glacier's movement rate. The combination of internal deformation and basal sliding means that glaciers move at different rates at different depths and locations. The ice moves fastest at the surface in the center of the glacier and slowest at the base and edges where friction with bedrock is greatest. This differential movement creates stresses that crack the surface ice into crevasses, deep fissures that can be hundreds of feet deep. These crevasses are hazards for anyone traveling on a glacier, but they all reveal the complex stress patterns within the ice. The erosive power of a glacier is intimately tied to its movement. A stationary mass of ice, no matter how thick, won't erode much. It's the movement, the constant grinding and scraping as the ice flows over bedrock, that accomplishes the work of valley carving. And because the entire thickness of the glacier is in contact with the valley floor and walls, all of it contributes to erosion. Rocks frozen into the base of the ice act like teeth on a saw or grit on sandpaper, wearing away the bedrock as the ice moves. The more rocks embedded in the ice, and the harder those rocks are, the more effective the erosion. Meltwater plays multiple crucial roles in glacial valley formation beyond just lubricating the glacier's base. Water can flow through cracks and tunnels in the ice, or along the interface between ice and bedrock. This flowing water carries sediment eroded by the glacier, transporting it away from the erosion site. Sometimes meltwater accumulates under pressure beneath the ice, emerging in powerful streams called glacial outburst floods when the water finds an escape route. These floods can move enormous volumes of sediment and even large boulders in a matter of hours, accomplishing in moments what might otherwise take years. Meltwater also exploits weaknesses in the bedrock. Water seeping into cracks can refreeze, expanding and widening those cracks, preparing the rock for plucking by the overriding glacier. This frost wedging is extremely effective at breaking apart rock, and when combined with the mechanical action of the moving ice, it can disintegrate even very hard rock formations. The debris carried by a glacier has a name: till. Glacial till is an unsorted mixture of materials, ranging from clay particles too small to see with the naked eye up to boulders the size of houses. Everything is mixed together because glaciers, unlike rivers, don't sort the material they carry by size. A river's current will carry clay particles in suspension, but drop boulders immediately. So river deposits are sorted with fine material separated from coarse. But glacial ice simply picks everything up and carries it along together, and when the ice melts, everything drops in place, creating till. Large boulders transported by glaciers, especially when they're carried far from their source and deposited in areas of very different rock type, are called glacial erratics. These can be spectacular, massive boulders sitting incongruously in landscapes where no similar rock exists anywhere nearby. Erratics are proof of glaciation because there's no other natural process that could have transported such enormous stones over such distances. The glaciers of the last ice age scattered erratics across much of northern North America and northern Europe, leaving a legacy of mystery stones that puzzled people for centuries before the reality of glaciation was understood. As a glacier moves through a valley, it not only erodes but also deposits. Along the edges of the glacier, rock debris accumulates, partly from material falling onto the ice from the valley walls, and partly from debris incorporated at the glacier's base and then carried to the surface by the ice's internal movement. These accumulations form ridges along the glacier's edges called lateral moraines. When two glaciers merge, their adjacent lateral moraines combine to form a medial moraine, a dark stripe of rock debris running down the center of the combined glacier. From above, a large glacier with multiple tributaries will show a complex pattern of medial moraines, each stripe recording where two ice streams met. At the glacier's terminus, where the ice is melting as fast as new ice arrives from upstream, debris accumulates in a ridge called a terminal moraine or end moraine. This marks the farthest extent of the glacier's advance. As the glacier retreats, it might pause at various points, building additional recessional moraines. These moraine ridges can survive for thousands of years after the ice is gone, marking out the former extent of glaciation across a landscape. Within the U-shaped valley itself, the floor is often covered with ground moraine, a layer of till deposited directly from the base of the glacier. This can be tens or even hundreds of feet thick, smoothing out some of the irregularities in the bedrock surface. The ground moraine often contains fine rock flour, sediment that has been ground so fine by glacial action that it's like powder. When streams carry this rock flour, it gives glacial meltwater a distinctive milky appearance. The carving of a glacial valley is not uniform. Glaciers erode more deeply in some areas than others, depending on ice thickness, the speed of ice flow, and the resistance of the bedrock. Where glaciers are thickest and moving fastest, erosion is most intense. Where tributaries join the main glacier, the combined ice creates extra erosive power, often carving the valley deeper at those junctions. Where bedrock is softer or more fractured, erosion proceeds more quickly than in areas of hard, massive rock. This differential erosion creates a valley floor with an irregular longitudinal profile. Instead of the smooth, concave profile typical of river valleys, glaciated valleys often have a more complex profile with sections of steeper gradient alternating with flatter sections. These irregularities are preserved after the ice melts, and they influence how water flows through the deglaciated valley. Glaciers also create landforms beyond the valley itself. At the head of a glacial valley, where the ice originates in a bowl-shaped hollow high on the mountainside, erosion creates a feature called a cirque. This is an amphitheater-shaped depression with a steep head wall, carved by the ice as it pulls away from the mountain face. Cirques are often separated by knife-edge ridges called arêtes, and where three or more cirques erode back into a mountain from different sides, they can create a pyramidal peak, a sharp mountain summit sculpted by glacial erosion from multiple directions. The Matterhorn in the Alps is perhaps the most famous example of such a glacially carved peak. The transformation of a landscape from river-dominated to glacier-dominated and then back to river-dominated after the ice melts creates valleys with complex histories. The current form of many mountain valleys reflects multiple episodes of glaciation, separated by warmer periods when rivers flowed through the valleys. Each glacial advance modified what came before, deepening and widening the valley, leaving behind new deposits and creating new landforms. Reading this history requires careful observation of valley shapes, deposits, and erosional features. But the story is there, written in the landscape for those who know how to read it. As your mind drifts, imagine standing at the head of a glacial valley, watching in time-lapse spanning millennia as ice accumulates, thickens, begins to flow. The valley slowly widens, deepens, the ice advances, reaches its maximum extent, then slowly, imperceptibly, begins to retreat. The valley is forever changed. Rift valleys, when Earth pulls apart. While rivers carve valleys from the top down, and glaciers reshape them through grinding and plucking, there is a third, profoundly different way that valleys form. Sometimes valleys are created not by erosion at all, but by the Earth's crust breaking and pulling apart. These are called rift valleys, and they are among the most dramatic geological features on the planet. Rift valleys form through tectonic processes. The movement and deformation of the lithospheric plates that make up Earth's outer shell. The Earth's surface is divided into several large plates and many smaller ones, all floating on the partially molten rock of the upper mantle beneath them. These plates move relative to each other, driven by convection currents in the mantle. Where plates collide, mountains are thrust up. Where plates slide past each other, earthquakes occur along the boundary. And where plates pull apart, rift valleys form. The process of rifting begins when tensional stresses stretch the crust, pulling it apart. This might occur because a mantle plume, a rising column of hot rock from deep within Earth, pushes up from below, causing the overlying crust to dome upward and crack. Or it might happen because plates are moving apart due to spreading at a mid-ocean ridge, or because of changes in the plate boundary forces. Whatever the cause, when the crust is stretched beyond its capacity to deform elastically, it fractures. These fractures create faults, breaks in the rock along which movement occurs. In a rift valley, the most important type of fault is a normal fault, where one block of crust slides downward relative to the adjacent block. Normal faults occur in extensional settings where the crust is being pulled apart. As the crust stretches and thins, blocks drop down along these faults, creating a depression. While the blocks on either side remain relatively elevated or even rise as the load is removed. The dropped block is called a graben, from the German word for ditch or grave, while the elevated blocks on either side are called horsts. A rift valley is essentially a series of grabens, creating an elongated depression that can extend for hundreds or even thousands of miles. The valley floor is the down-dropped block, and the valley walls are the fault scarps, the steep slopes created by the displacement along the faults. Unlike river or glacial valleys that form through subtraction of material, rifted valleys form through a movement of crustal blocks. The material doesn't go anywhere. It just drops down, creating the depression. The most spectacular example of a rift valley system on Earth is the Great Rift Valley in East Africa. This enormous feature stretches more than 3,000 miles from the Red Sea in the north through Ethiopia, Kenya, Tanzania, and beyond. It is actually not a single continuous valley, but a system of interconnected rifts, all representing places where the African continent is being pulled apart by tectonic forces. In some places, the Great Rift Valley is more than 30 miles wide and several thousand feet deep. The valley floor contains a string of lakes, including some of the largest and deepest lakes in Africa, such as Lake Tanganyika and Lake Malawi. These lakes occupy the deepest parts of the rift, places where the crust has dropped the farthest. The valley walls are marked by spectacular escarpments, steep cliffs that mark the fault lines along which the crust has fractured. The East African Rift is an active rift system, meaning the process of rifting is ongoing. The crust is still stretching and breaking, earthquakes still occur along the faults, and in some areas, volcanic activity accompanies the rifting. This volcanism occurs because as the crust stretches and thins, it creates pathways for magma from the mantle to rise to the surface. Some of Africa's most famous volcanic mountains, including Mount Kilimanjaro and Mount Kenya, are associated with rift volcanism. Rift valleys represent the first stage in the breakup of a continent. If rifting continues for long enough, the continent will eventually split completely, and a new ocean basin will begin to form between the separating fragments. The Red Sea, which lies at the northern end of the East African Rift system, represents a more advanced stage of this process. Here, rifting has proceeded to the point where the Rift Valley has dropped below sea level and has been flooded by ocean water, creating a narrow sea between Africa and Arabia. Given another few tens of millions of years, East Africa may similarly split from the rest of the continent, with a new ocean forming in the Rift Valley. This is actually how most ocean basins form. The Atlantic Ocean, for example, began as a rift valley about 200 million years ago when the supercontinent Pangaea started to break apart. What began as a relatively narrow rift valley in the interior of the supercontinent eventually widened, was flooded by seawater, and became the vast ocean we know today. The mid-ocean ridges that run down the center of ocean basins are the underwater continuation of the rifting process, where new oceanic crust is continuously created as the plates spread apart. Not all rift valleys become oceans. Sometimes rifting begins, but then stops, leaving behind what's called a failed rift or alacogen. The crust has been stretched and faulted, creating a rift valley, but the process doesn't continue to the point of complete continental breakup. Failed rifts can persist in the continental interior as zones of weakness, and they often influence the locations of rivers and other features. The Mississippi River, for example, follows the course of an ancient failed rift called the Real Foot Rift, which formed about 500 million years ago when North America nearly split apart, but the rifting stopped before an ocean could form. Rift valleys have a very different character from erosional valleys. While river and glacial valleys typically follow pre-existing topographic lows or zones of weaker rock, rift valleys can cut across the grain of the landscape, forming wherever the tectonic stresses cause the crust to fracture. Rift valleys are typically very straight, following the trend of the underlying faults, whereas erosional valleys wind and meander according to the path of least resistance for flowing water or ice. The walls of a rift valley are often marked by multiple parallel fault scarps, creating a step-like profile. Each scarp represents a different fault, and the rift valley floor is actually a mosaic of tilted blocks that have dropped to various levels. Over time, erosion attacks these fault scarps, wearing them back and depositing sediment on the valley floor. Rivers may develop along the valley floor, taking advantage of the topographic low created by rifting. So, while the valley's origin is tectonic, its subsequent evolution may include significant erosion and sediment deposition, blending tectonic and erosional processes. Rift valleys are not just terrestrial features. They exist on other planets and moons as well. Mars has enormous rift valleys, including Valle Marineris, a rift system that dwarfs anything on Earth. Venus has rift features. Even Jupiter's moon Europa shows evidence of crustal fracturing and possible rifting beneath its icy shell. These extraterrestrial rifts remind us that the process of crustal stretching and breaking is fundamental to how rocky planetary bodies evolve. On Earth, rift valleys are important for several reasons beyond their spectacular scenery. They create topographic lows where lakes can form and where sediment accumulates, building up thick sequences of sedimentary rocks that preserve records of past environments. They create zones of volcanic activity that can enrich soils and create dramatic landscapes. And they represent places where continents are actively changing, where the map of the world is being redrawn, slowly but inexorably, by the tectonic forces at work beneath our feet. As you drift towards sleep, imagine the Earth's crust stretching like a sheet being pulled from both ends. It resists at first, but eventually the strain is too great. Fractures form, blocks drop, a depression opens, deep and steep-walled. Rift Valley, the Earth pulling itself apart. The evolution of valley shapes. Valleys are not static. They change over time, evolving through stages as the processes that form them continue to work. Understanding this evolution helps us see valleys not as fixed features, but as dynamic landforms in constant transformation. This is particularly clear when we examine how valleys change from youth through maturity to old age, though these terms should be understood as describing stages in valley development rather than absolute ages. A young valley is typically narrow and steep-sided. If it's a river valley, the stream is actively cutting downward, eroding vertically more than laterally. The valley has a pronounced V shape in cross-section, and the gradient is steep. Waterfalls and rapids are common because the river hasn't yet smoothed out irregularities in the underlying rock. The valley floor is narrow, often occupied entirely by the river channel with little or no floodplain. Tributaries join the main valley at steep angles, often creating hanging valleys where smaller streams plunge down to join the main river. As a valley matures, its character changes. The river continues to cut down, but as the gradient decreases, more energy goes into lateral erosion, swinging the river back and forth across the valley floor. The valley widens. The floor becomes broader as the river deposits sediment during floods, building up a floodplain. The V shape may persist, but it's a broader, gentler V. Waterfalls are worn away or reduced to rapids. Tributaries have cut down to match the level of the main valley, eliminating hanging valleys. The valley walls are still distinct, but weathering and mass movement have reduced their steepness somewhat. In old age, a valley becomes quite broad relative to its depth. The river meanders widely across an extensive floodplain, creating oxbow lakes and natural levees. The valley walls are far apart and have gentle slopes, worn back by prolonged weathering and erosion. The gradient is very low, and the river flows sluggishly. Most of the erosion is lateral, widening the valley further with very little vertical cutting. The landscape has a much subdued relief compared to the young valley's dramatic topography. This evolutionary sequence is not inevitable or irreversible. If the land is uplifted by tectonic forces, an old valley can be rejuvenated, given a new lease on erosive life as the increased gradient boosts the river's power. The river responds by cutting down again, creating a valley within a valley. The old, broad floodplain may be left high above the new channel as a terrace, a flat bench on the valley side that preserves the former valley floor. Rivers that have been rejuvenated often show entrenched meanders, where the looping curves typical of an old river's floodplain are incised deeply into bedrock as the river cuts down. The concept of base level is crucial to understanding valley evolution. As mentioned earlier, base level is the lowest point to which a river can erode. Rivers approach but never quite reach their base level, because as gradient decreases, so does erosive power. The longitudinal profile of a graded river is one that is in equilibrium with its discharge and sediment load, creating a smooth curve from source to mouth that represents a balance between erosion and deposition. Changes in base level have profound effects on valleys. If sea level drops, perhaps because water is locked up in glacial ice during an ice age, rivers suddenly find themselves with a lower base level. Their mouths are now elevated above the new sea level, and they respond by cutting down, eroding downward to adjust to the new base level. This downcutting propagates upstream, a wave of erosion moving up the river system. The valley deepens, and features like waterfalls may form where the wave of downcutting encounters resistant rock. Conversely, if sea level rises, the river's mouth is drowned. Seawater floods the lower valley, creating an estuary. The river now has a higher local base level, and it responds by depositing sediment, filling the drowned valley with alluvium. The valley transitions from an erosional to a depositional environment. These shifts between erosion and deposition in response to changing base level are recorded in the deposits and landforms preserved in and around valleys, providing clues to past environmental changes. Some valleys develop broad, flat floors through a different process. These flat-floored valleys result when a river reaches a state of dynamic equilibrium, where the amount of sediment it receives from upstream matches the amount it can transport away. The river then swings back and forth across the valley floor, depositing sediment during floods but neither significantly deepening nor widening the valley. Over time, the floor becomes mantled with alluvium, creating a surface that is flat and nearly level, ideal for agriculture and settlement. The Nile Valley is a classic example of a flat-floored valley. For much of its length through Egypt, the Nile flows through a valley with steep walls but a broad, flat floor covered with fertile alluvium. This valley has evolved over millions of years, and its current form reflects the balance between sediment supply from upstream erosion, sediment transport by the river, and deposition on the valley floor during the river's annual flood cycle. Canyons and gorges represent a special type of valley where vertical erosion has far outpaced lateral erosion and weathering of the valley walls. These deep, narrow valleys form in several settings. One is where a river is cutting rapidly into resistant rock, perhaps in response to rapid uplift or a drop in base level. The hard rock resists weathering, so the valley walls remain steep and close together even as the river cuts down. The Grand Canyon is the most famous example, where the Colorado River has incised more than a mile down into layered sedimentary rocks, while the arid climate limits the weathering that would widen the valley. Canyons can also form in areas of horizontal rock layers where water exploits weaknesses. Slot canyons, those astonishingly narrow, deep gorges found in places like the Colorado Plateau, form when flash floods roar through cracks in sandstone, eroding downward much faster than the walls erode laterally. The result is a canyon so narrow that you can touch both walls with outstretched arms, yet hundreds of feet deep. The evolution of valley form is also influenced by climate. In wet climates, weathering is more rapid, and vegetation stabilizes slopes, leading to valleys with gentler sides. In dry climates, weathering is slower. Mechanical weathering dominates over chemical weathering, and vegetation is sparse, leading to valleys with steeper walls. The same river in the same type of rock might create different valley profiles depending on whether it flows through a humid or arid region. Rock type matters enormously. Valleys carved in hard, massive rocks like granite tend to be narrow with very steep walls because the rock resists weathering and maintains steep slopes. Valleys in softer, layered sedimentary rocks tend to be broader with gentler slopes because the rock weathers more easily, and mass movements are more frequent. Valleys in areas of varied rock types often have irregular profiles, with sections of steep walls where hard rock resists erosion, alternating with sections of gentler slopes where softer rock has weathered back. The time it takes for a valley to evolve through these stages varies enormously depending on rock resistance, climate, erosion rate, and tectonic setting. In some rapidly uplifting mountain ranges with high rainfall, valleys can deepen by hundreds of feet in just a few 100,000 years. In Stonepeni, low-lying areas with resistant rock and little rainfall, valleys may change almost imperceptibly over millions of years. What matters for our peaceful journey toward sleep is recognizing that valleys, like so much in nature, are works in progress. They are not finished products, but ongoing processes, always adjusting, always responding to the interplay of uplift, erosion, climate, and time. The valley you walk through today is different from the valley that existed 1,000 years ago, and it will be different again 1,000 years hence. The change is too slow to see, but it's always happening. Let yourself relax into the rhythm of geological time. Millennia pass like seconds. Valleys deepen, widen, evolve. The landscape is fluid when viewed across spans of time sufficient to perceive the change. Everything flows. Everything transforms. Special valley types and features. Beyond the basic categories of river, glacial, and rift valleys, there are many specialized valley types and features that deserve exploration. These add texture and detail to our understanding of how valleys form and what they can tell us about Earth's processes. Hanging valleys are among the most dramatic features of glaciated landscapes. These are tributary valleys whose floors are elevated well above the floor of the main valley they join. They form because the main valley contained a much larger, thicker glacier than the tributary, and the main glacier eroded more deeply. When the ice melts, the tributary valley is left stranded high on the wall of the main valley. Any stream that forms in the hanging valley must plunge down to reach the main valley floor, creating waterfalls that can be spectacular. Yosemite Valley in California is renowned for its hanging valleys and waterfalls, including Bridal Veil Fall and Yosemite Falls, each cascading from a tributary valley left hanging by glacial erosion. Dry valleys are valleys that no longer contain permanent streams or rivers. These can form in several ways. In limestone regions, water may infiltrate the porous and soluble rock, creating underground drainage systems. The valley that once contained a surface stream is now dry, with water flowing through caverns and passages beneath. England's Mendip Hills and Yorkshire Dales contain many such dry valleys, carved when drainage was at the surface but now abandoned as water has found subterranean routes. In formerly glaciated regions, dry valleys may be valleys that were carved by glacial meltwater during deglaciation but now lack sufficient water flow to maintain a permanent stream. In arid regions, valleys may carry water only during rare floods, remaining dry for months or years at a time. These ephemeral streams can be quite powerful during flash floods, moving large volumes of sediment and continuing the work of valley erosion even though they flow only sporadically. The term wadi is used in Arabic-speaking regions for such ephemeral valleys, while in the American Southwest they're often called arroyos or washes. These valleys are distinctive because their form reflects sporadic but intense flows rather than the continuous erosion of a permanent stream. Their floors are often covered with coarse sediment deposited during floods, and their walls can be quite steep where flash floods have undercut them. Submarine valleys extend valley systems offshore, often at the mouths of major rivers. These submarine canyons can be enormous, cutting through the continental shelf and slope to depths of thousands of feet below sea level. Some formed when sea levels were much lower during glacial periods, and rivers extended across the exposed continental shelf, carving valleys that were later submerged as ice melted and seas rose. Others form through processes unique to the submarine environment, including turbidity currents, underwater avalanches of sediment-laden water that race down the continental slope, eroding the seafloor. The Hudson Canyon off New York, the Monterey Canyon off California, and the Congo Canyon off West Africa are among the many spectacular submarine valleys that extend river systems far out into the ocean. These features are important conduits for sediment transport from land to the deep ocean basins, and they create unique habitats for marine life. Volcanic valleys form in regions of volcanic activity, often when lava flows down existing valleys, or when volcanic activity creates new topography that channels water into new drainage paths. On the flanks of large volcanoes like those in Hawaii, valleys have been carved by streams cutting into lava flows. These valleys can be quite young in geological terms, thousands rather than millions of years old, yet already showing well-developed valley characteristics. Some valleys result from the collapse of surface material into voids below, a process particularly common in areas of limestone or other soluble rock. These collapse valleys or karst depressions can be quite deep and steep-walled, forming suddenly when the roof of an underground cavern gives way. In some regions, entire landscapes are dominated by karst features, with valleys, sinkholes, and collapsed depressions creating extremely irregular topography. The concept of a compound valley is important for understanding many real-world valleys. Most valleys are not formed by a single process acting alone, but by multiple processes acting in sequence or simultaneously. A valley might be carved initially by a river, then widened and deepened by glaciers during ice ages, then partially filled with sediment by post-glacial rivers. Its current form reflects this complex history, and careful observation can often tease apart the different stages. Valley trains refer to the long stretches of sediment deposited in valleys by glacial meltwater. As glaciers melt, they produce enormous volumes of water carrying heavy loads of sediment. This sediment is deposited in the valley floor, creating an extensive outwash plain that can extend for many miles downstream from the glacier's terminus. These valley trains are common features in formerly glaciated regions, and they often provide fertile, well-drained soils. Terraces are step-like features on valley sides that represent former valley floors. They form when a river cuts down into its own floodplain, leaving remnants of the former floor elevated above the new channel level. Terraces can form due to climate changes that alter stream discharge, due to tectonic uplift that rejuvenates the river's erosive power, or due to changes in base level. Multiple terraces at different heights record multiple episodes of valley floor formation and subsequent incision, creating a staircase that preserves the valley's evolutionary history. These various valley types and features remind us that valleys are far more diverse than any simple classification might suggest. Each valley is unique, reflecting the particular combination of rock types, climate, tectonic setting, and erosional processes that have shaped it. Learning to recognize these features and understand what they signify allows us to read valleys like books, extracting the stories they tell about Earth's past and the ongoing processes that continue to modify them. As your breathing deepens and slows, picture the variety of valleys across the world. Narrow gorges, broad floodplains, hanging valleys with waterfalls, dry valleys and deserts, each one different. Each one shaped by its own unique history, the forces behind the forms. The shape of any particular valley results from the interaction of multiple factors. Understanding these factors helps us see why valleys look the way they do, and why similar processes can produce different results in different settings. Let's explore the key forces and conditions that control valley formation and evolution. Rock type and structure exert fundamental control over valley characteristics. Hard, resistant rocks like granite, quartzite, and basalt erode slowly, allowing valleys to maintain steep walls. Rivers cutting through such rocks create narrow, deep gorges. Weathering and mass wasting are slow, so the valley walls retreat only gradually, even as the river continues to cut down. The result is a valley with dramatic relief, often with near vertical walls rising high above the valley floor. In contrast, soft rocks like shale, mudstone, and poorly cemented sandstone erode much more readily. Rivers cut through them more easily, but weathering and mass movements also attack the valley walls more effectively. The valley widens as fast or faster than it deepens, producing valleys with gentler slopes and broader floors. The relief may be considerable, but the profile is much less dramatic than in resistant rock. The structure of the rock also matters. Rocks that are highly fractured, with many joints and cracks, erode more easily than massive, unfractured rock. Glacial plucking is particularly effective in well-jointed rock, where the ice can exploit the natural planes of weakness. Valleys in complexly folded or faulted terrain often have irregular shapes, with sudden changes in width or direction, where the valley crosses different rock types or structural features. Layered sedimentary rocks create distinctive valley forms when the layers are tilted or gently inclined. Rivers may follow the weaker layers, creating valleys with one steep wall cut across hard layers and one gentle wall that slopes along the bedding. These asymmetric valleys are common in areas of tilted sedimentary rocks. Climate profoundly influences valley development. In humid climates with abundant rainfall, rivers carry more water and erode more vigorously. Chemical weathering is more effective, breaking down rock more rapidly. Vegetation is dense, stabilizing slopes and reducing mass movements. The overall effect is valleys that are wider relative to their depth with well-vegetated slopes. In arid climates, rivers are often ephemeral, flowing only during occasional storms. Chemical weathering is minimal, and mechanical weathering dominates. Vegetation is sparse, providing little stabilization, so mass movements can be sudden and dramatic during rare rain events. Valleys in arid regions often have very steep, bare rock walls and relatively narrow forms because weathering is slow, and lateral erosion is limited. In very cold climates, frost action becomes a dominant weathering mechanism. Water freezing in rock cracks expands, wedging the cracks wider and eventually shattering the rock. This frost wedging can be extremely effective, reducing solid rock to piles of angular fragments. Valleys in periglacial regions, areas too cold for glaciers but where freezing and thawing are common, often have slopes mantled with these frost-shattered rock fragments. Tectonic activity interacts with erosion in complex ways. The paradox mentioned earlier bears repeating because it's so important. The most rapid erosion occurs in areas of most rapid uplift. This seems counterintuitive. If land is being pushed up rapidly, shouldn't it be getting higher rather than being eroded away? But uplift creates high relief, steep slopes, and steep river gradients. These steep gradients give rivers enormous erosive power. So, even though land is being lifted up, rivers cut down just as fast or faster, maintaining steep valleys and high erosion rates. The Himalayas provide a spectacular example. This mountain range is being uplifted rapidly, several millimeters per year in places, as the Indian subcontinent continues to collide with Asia. The uplift creates enormous relief, and the rivers draining the Himalayas have correspondingly steep gradients. These rivers, including the Indus, Ganges, and Brahmaputra, are among the most erosive on Earth, carrying away billions of tons of sediment annually. The valleys they carve are deep, often several thousand feet or more, despite the ongoing uplift. The landscape is in a dynamic balance between uplift, trying to raise it, and erosion, trying to wear it down. This balance is described by the concept of equilibrium in a landscape at more. Equilibrium, erosion rates match uplift rates, so the overall elevation remains relatively constant, even though both processes are active. The landscape is in a steady state, continuously being uplifted and continuously being worn down, but maintaining an average elevation. Real landscapes are rarely in perfect equilibrium. They're constantly adjusting to changes in uplift rates, climate, sea level, and other factors. But the concept helps us understand how dramatically uplifted landscapes can persist without being worn down to flat plains, and how erosion can proceed rapidly in areas of high relief. The size of a drainage basin influences valley characteristics. A large drainage basin collects water from a vast area, feeding a major river with high discharge. Such rivers have greater erosive power and can carve larger, deeper valleys. The Amazon, Mississippi, Nile, and other great rivers drain in enormous basins and have correspondingly massive valleys. Small drainage basins produce modest streams with limited erosive capacity, carving smaller valleys. Sediment load also matters. A river carrying a heavy sediment load must expend energy transporting that sediment, reducing the energy available for erosion. A river with little sediment, carrying only clear water, can focus all its energy on eroding the channel. This is why dam construction often leads to increased erosion downstream. The dam traps sediment, so the water released below the dam is sediment-starved and hungry for sediment to transport. It responds by eroding its channel more vigorously, sometimes cutting down many feet in just a few decades. Time is perhaps the ultimate factor. Given enough time, even the slowest erosion will produce deep valleys. Given sufficient time, even the hardest rocks will wear away. The Grand Canyon required roughly 6 million years to reach its present depth. That seems an almost inconceivable span, yet it's only a tiny fraction of Earth's age. The processes shaping valleys have been at work for billions of years, and they'll continue for billions more, always sculpting, always modifying, always carving Earth's surface into valleys and the highlands that separate them. All these factors intertwine. Rock type influences how climate affects erosion. Climate influences the type and vigor of weathering. Tectonic activity provides the relief necessary for vigorous erosion. Time allows small effects to accumulate into major landscape changes. Understanding valley formation means understanding how all these factors work together, creating the specific combination that produces each unique valley. Let yourself sink deeper. Feel the weight of geological time. Forces acting, rock yielding, valleys deepening. All of it proceeding according to natural laws, processes that have operated since continents first rose above the oceans, and will continue until the sun grows dim. Famous valleys, stories written in stone. Some valleys have become famous, iconic, landmarks that draw millions of visitors and inspire countless images. These valleys are worth exploring individually because they beautifully illustrate the principles we've discussed and because they show the stunning results when valley-forming processes work at grand scales. The Grand Canyon of the Colorado River in Arizona is perhaps the world's most famous valley. This vast gorge stretches for over 270 miles, reaches widths of up to 18 miles, and plunges more than a mile in depth. The canyon exposes nearly 2 billion years of Earth's geological history in the layers of rock visible in its walls, creating a geological textbook written in stone. The Grand Canyon is primarily a river-carved valley. The Colorado River has been cutting down into the Colorado Plateau for roughly the past 6 million years, incising through layer after layer of sedimentary rock. The canyon's great depth results from several factors working together. The Colorado Plateau was uplifted tectonically, raising the region thousands of feet and giving the Colorado River a steep gradient and enormous erosive power. The climate is arid, so weathering and lateral erosion of the canyon walls is slow, allowing the canyon to maintain its narrow, steep-walled form, even as the river cuts deeper. The rocks include hard, resistant layers like limestone and sandstone that can support near-vertical cliffs. The result is a canyon of stunning proportions, its walls stepping down in great cliffs and slopes corresponding to alternating hard and soft rock layers. The Colorado River still flows at the bottom, a ribbon of water that seems impossibly small to have carved such an enormous chasm. But given millions of years and billions of tons of sediment carried away, grain by grain, even a modest river can excavate a canyon that seems almost beyond imagination. Yosemite Valley in California provides a classic example of glacial valley formation. This U-shaped valley in the Sierra Nevada mountains was carved by glaciers that repeatedly advanced down the valley during ice ages over the past few million years. The valley is about 7.5 miles long, roughly 1 mile wide, and its walls rise 3,000 to 4,000 feet nearly vertical in places. The granite cliffs of Yosemite, including famous features like El Capitan and Half Dome, were shaped by glacial erosion. The valley's flat floor is mantled with sediment left by the glaciers and deposited by the Merced River that now flows through the valley. Hanging valleys mark where tributary glaciers join to the main valley glacier, and spectacular waterfalls cascade from these hanging valleys, including Yosemite Falls, one of the tallest waterfalls in North America, dropping more than 2,400 feet. Yosemite beautifully illustrates the transformation from V-shaped river valley to U-shaped glacial valley. Before glaciation, the Merced River had carved a typical V-shaped valley into the granite. When climate cooled and glaciers formed, ice filled the valley, widening and deepening it dramatically. The ice transformed the sharp V into a broad U, truncated the interlocking spurs, created the hanging valleys, and left behind the spectacular landscape we see today. The glaciers last retreated about 10,000 years ago, but their signature is unmistakable in every aspect of the valley's form. The Great Rift Valley of East Africa is the most spectacular example of a rift valley system on Earth. Extending more than 3,000 miles from the Red Sea through Ethiopia, Kenya, Tanzania, and beyond, this system represents an active continental rift where Africa is slowly being pulled apart. In some places, the valley is more than 30 miles wide and drops several thousand feet below the surrounding plateau. The valley's floor contains numerous lakes, including Lake Tanganyika, one of the world's deepest lakes, and Lake Victoria, though Victoria lies between two branches of the rift rather than in it. Volcanic mountains like Kilimanjaro and Meru rise along the rift, testament to the volcanic activity that accompanies rifting. The valley walls are marked by great fault scarps, and earthquakes regularly remind inhabitants that this is a geologically active region where the crust is still stretching and breaking. The East African Rift provides a window into how continents break apart. Millions of years in the future, if rifting continues, the eastern part of Africa may separate completely, becoming an island like Madagascar, with a new ocean forming in what is now the Rift Valley. This is not idle speculation. The same process has created every ocean basin on Earth, and the East African Rift is our best opportunity to observe the early stages of continental breakup. The fjords of Norway are drowned glacial valleys, U-shaped valleys that extend below sea level and have been flooded by the ocean. These long, narrow sea inlets are surrounded by towering cliffs that rise directly from deep water, creating scenery of breathtaking grandeur. Sognefjord, Norway's longest and deepest fjord, extends more than 120 miles inland and reaches depths of more than 4,000 feet below sea level. Fjords form when glacial valleys are carved below sea level, and then, after the ice melts and sea level rises, are inundated by ocean water. The great depth of fjords reflects the enormous erosive power of the glaciers that carved them. The steep walls and relatively straight courses are typical of glacial valleys. Hanging valleys occur along the fjord walls, with waterfalls plunging directly into the sea. Fjords are found in many formerly glaciated coastal regions, including Alaska, Chile, New Zealand, and Antarctica, but Norway's fjords are particularly famous and extensive. They provide spectacular evidence of just how deeply glaciers can erode, cutting valleys thousands of feet below sea level before melting away and leaving the valleys to be claimed by the ocean. The Kali Gandaki Gorge in Nepal claims to be the world's deepest valley. This river valley lies between two 8,000-meter peaks, Dhaulagiri and Annapurna, creating a total relief of about 6 kilometers from the peaks to the valley floor. The valley is remarkably narrow given its enormous depth, creating one of the most dramatic valley profiles anywhere on Earth. The Kali Gandaki Gorge illustrates the relationship between tectonic uplift and erosion. The Himalayas are rising rapidly due to the collision between the Indian and Asian continents, and the rivers draining these mountains are cutting down just as rapidly. The result is deep, steep-walled valleys in regions of maximum uplift. The gorge also shows how rivers can maintain their courses even as mountains rise around them, cutting down at the same rate the land is lifted up, a process called antecedent drainage. These famous valleys and many others remind us that valley formation, while slow by human standards, can produce some of the most spectacular landforms on Earth. They are monuments to the power of gradual processes acting over immense spans of time, to the creativity inherent in natural systems, and to the dynamic nature of Earth's surface. Each tells a story, and learning to read these stories is one of the great pleasures of understanding geology. Your mind can rest now among these grand landscapes. Imagine standing at the rim of the Grand Canyon as sunset paints the cliffs in shifting shades of red and gold. Imagine the silence of Yosemite Valley in winter, snow covering the floor, the waterfalls frozen into ribbons of ice. Imagine looking up from the depths of a Norwegian fjord at cliffs rising thousands of feet into mist. Let these images carry you deeper into peaceful rest. Valleys and the flow of time. Valleys serve as archives of Earth's history. The rocks exposed in valley walls, the sediments deposited on valley floors, the shape of the valley itself, all contain information about past events, past climates, and past processes. Learning to read these archives is one of the most powerful ways we have of understanding Earth's history. The rocks exposed in a valley's walls may have formed hundreds of millions of years ago, in ancient seas or deserts or volcanic landscapes utterly different from the modern world. As a valley deepens, it cuts down through successively older layers, exposing a cross-section through geological time. The Grand Canyon is famous for this, with rocks at the bottom dating back nearly 2 billion years. Walking from the rim to the river is like walking backward through time, each layer representing a different chapter in Earth's history. These rocks contain fossils, the preserved remains of ancient organisms that tell us what life was like when the rocks formed. They contain minerals and chemical signatures that reveal information about ancient climates, ocean chemistry, and atmospheric composition. They show evidence of past volcanic eruptions, earthquake-generated deposits, desert environments, deep oceans, tropical reefs, all preserved in the geological record exposed by valley erosion. The shape of a valley itself records information. A U-shaped valley tells us that glaciers once occupied this region, even if no ice has existed here for thousands of years. The presence of hanging valleys confirms that glaciation was extensive and involved multiple tributaries. The smooth, polished rock surfaces called glacial polish, the scratches called striations, the deposits of unsorted till. All these features persist long after the ice is gone, recording its former presence. Terraces on valley sides record former valley floor positions, which in turn record information about past discharge, past climate, and past base levels. Each terrace formed when the valley floor was at that elevation. The river then cut down, abandoning the old floodplain and leaving it as a terrace. The elevation and age of terraces can be determined, and from this information scientists can reconstruct the history of valley incision, correlating it with climate changes, tectonic events, or other factors that cause the river to alter its behavior. Sediments deposited in valleys are like pages in a book. Each layer represents a certain time period, and the characteristics of the sediment reveal the environmental conditions when it was deposited. Coarse gravels suggest high energy flow, perhaps during floods or in steep mountain streams. Fine silts and clays suggest quiet water, perhaps in a floodplain lake or slow-moving river. Organic rich layers might represent times when vegetation was abundant. Layers of volcanic ash record volcanic eruptions, providing time markers that can be dated and correlated across large regions. By carefully studying these sediments, scientists can reconstruct past environments with remarkable detail. They can determine whether the climate was wet or dry, warm or cold. They can tell when forests grew where now there is desert, or when glaciers advanced where now rivers flow. The sediments in valleys are archives of climate change, recording the ice ages, the warm periods between them, and the complex climate variability that characterizes Earth's history. Valleys also record tectonic history. Faulting and folding of rocks in valley walls reveal past earthquakes and mountain-building episodes. Offset stream channels and terraces can reveal how much movement has occurred along faults. Variations in valley depth and shape may correlate with variations in rock strength or structural features, revealing hidden aspects of the geological architecture beneath the surface. The persistence of valley forms is remarkable. Even after the processes that carved them cease, valleys remain recognizable for immense periods. U-shaped valleys carved during the last ice age, which ended about 10,000 years ago, look nearly as fresh today as when the ice melted. River channels abandoned millions of years ago may still be traceable in ancient sedimentary rocks. This persistence means valleys are not just temporary features but enduring elements of the landscape that can survive for tens or hundreds of millions of years, outlasting the mountains from which they were carved. Yet valleys also change. Rivers gradually fill their valleys with sediment, raising the valley floor. Landslides episodically modify valley walls. Renewed uplift can rejuvenate valleys, causing rivers to cut down again. Valleys are simultaneously archival records of the past and dynamic features responding to ongoing processes. They are both fixed and fluid, preserving history while continuing to evolve. This dual nature makes valleys fascinating subjects for study. They are legible, offering clues that can be decoded to reveal their history. But they are also still being written, with new pages being added even as we read the old ones. Understanding valleys means understanding both what they preserve and how they continue to change. For us, drifting towards sleep, valleys are reminders of time's vastness and the patient work of natural processes. A valley 1,000,000 years old is ancient by any human measure, yet it's young in geological terms. The processes that shaped it are still active, still carving, still modifying. The story continues, written in rock and water, ice and earth, unfolding across spans of time that dwarf human history. Let your thoughts drift like sediment settling in quiet water. Let time expand until 1,000 years passes in a heartbeat. Valleys deepen. Landscapes transform. The earth renews itself through endless cycles of uplift and erosion, creation and destruction. All of it part of the grand, slow dance of geological time, the endless sculpture. As we approach the end of our journey through the formation of valleys, let yourself settle into complete rest. We've traveled through deep time and across continents, exploring how rivers patiently carve V-shaped valleys, how glaciers grind their way through mountain terrain, creating U-shaped troughs, and how the Earth's crust itself can crack and pull apart to form rift valleys. We've seen how rock type and climate and tectonic forces interact to shape valleys in endlessly varied ways, and how valleys serve as archives of Earth's history, recording past climates and processes in their forms and deposits. The story of valleys is ultimately a story about change. Nothing on Earth's surface is permanent. Mountains rise only to be worn down. Valleys form and deepen, then are filled with sediment or uplifted and transformed. The landscape is in constant flux, though the changes occur so slowly that they're invisible to us in our brief lifetimes. Only by extending our perspective across thousands or millions of years can we perceive the flow, the endless sculpture of Earth's surface by water, ice, and tectonic forces. There is something deeply peaceful in this understanding. The valleys that seem so solid and permanent are actually fluid when viewed across geological time. The mountains that appear eternal are temporary features destined to be worn away and replaced by others. Everything flows. Everything changes. And the processes that drive this change, erosion and uplift, destruction and creation, are as natural and inevitable as the tides or the seasons. If you found comfort in this exploration of how valleys form, I invite you to like this video and subscribe to the Sleepy Science Society. Your support helps more people discover these gentle journeys into science, these peaceful explorations that blend learning with rest. Feel free to leave a comment sharing your thoughts, or suggesting topics you'd like to explore in future videos. The community that gathers here is part of what makes this channel special, and your participation matters. But for now, let all of that go. You've done enough thinking for tonight. You've explored vast landscapes and deep time. You've followed rivers cutting through stone and glaciers grinding down valleys. You've watched continents pull apart and valleys form in the gaps. Your mind has traveled far, and now it's time to rest. Let your body sink deeper into your bed. Feel the support beneath you, solid and reliable. Let your shoulders drop. Let any tension in your face dissolve. Your jaw can relax. Your tongue can rest easy in your mouth. There's nothing you need to do, nowhere you need to go. The valleys of the world will continue their slow evolution, whether you're thinking about them or not. The rivers will keep flowing. The glaciers, where they still exist, will keep moving. The tectonic plates will continue their slow dance. All of these processes proceed without effort, without hurry, without concern. They simply happen, following the natural laws that govern matter and energy, water and ice, rock and time. There's a lesson in that, a reminder that so much of what happens in the universe happens naturally, without forcing, without striving. The valley doesn't try to form. It simply does, as water flows and rock yields, as ice moves and erosion works its patient magic. You too can stop trying, stop striving. Let yourself simply be, like a valley floor where sediment settles, where water pools quietly, where everything finds its level naturally. There's no effort in sleeping. It's a letting go, a release, a surrender to natural rhythms that know better than your conscious mind what you need. Picture a valley at dawn. Mist rises from a river winding along the valley floor. The valley walls rise on either side, still in shadow, but the eastern sky is brightening. Birds begin to sing. The air is cool and fresh. The valley is waking, but slowly, peacefully, without rush. There's time. There's always time. You're in that valley now, in your mind. You're lying on the soft grass beside the river. The water flows past with a gentle sound. The mist swirls around you, cool against your skin. The valley walls rise protectively on either side, sheltering you, holding you safe. You are held by the earth itself, cradled in a valley carved by patient forces across immeasurable time. The river knows where it's going. It flows toward the sea, following the gradient, always downhill, never struggling, never questioning. It simply flows. You can be like the river. You can flow toward sleep, following the natural gradient of your tiredness, your body's need for rest. You don't have to force it. You don't have to try. Just let yourself flow, like water finding its way, natural and easy. The valley is quiet now. The birds have finished their dawn chorus. The mist is lifting. The sun touches the highest peaks, turning them gold. But down here in the valley, it's still cool and shadowed, perfect for rest. You can stay here as long as you like. This valley is yours. It exists for you, a place of perfect peace and safety. Feel the earth beneath you, solid and ancient, a valley floor deposited grain by grain over thousands of years. Feel the air around you, cool and still. Hear the river's gentle song. Everything is calm. Everything is exactly as it should be. Your breathing has slowed to match the rhythm of the river, in and out, like water flowing. Each breath takes you deeper, further into rest. Each exhalation releases more tension, more thought, more wakefulness. You're drifting now, floating between waking and sleep in that peaceful liminal space where everything is soft and quiet. The valley holds you. The earth holds you. Time stretches out, endless and patient. There is nothing you need to do, nothing you need to remember. The valleys of the world are being carved whether you're aware of it or not. The processes continue. Life continues. And you can let go, knowing that everything will be there when you wake. But for now, sleep. Let the valley cradle you. Let the sound of the river carry you away. Let the cool air and the soft earth and the protective walls surround you in perfect, complete safety. You are held. You are safe. You can rest. Sleep now. Deep and peaceful sleep. The valleys are still being formed, slowly, patiently, across the face of the earth. And you are part of it all. Part of the great flowing system of change and rest, erosion and deposition. Waking and sleeping. Everything in its time. Everything in its place. Good night.